All right, so this is part 3 of our coverage of section 5.2. We're going to talk about some more properties, this time of the definite integral. So the first one is this. If you remember at the beginning when I defined the definite integral, I said you want to think of the lower limit of integration as the smaller of these two numbers and the upper limit of integration as the larger of these two numbers. And then I said, even though we're kind of thinking of that in the general case, that's not actually a requirement, because if you think of the definition of the definite integral as just a formula of sorts, then you can just plug these numbers directly into that formula, regardless of which one is bigger than the other. And we get this interesting property here. If you take the integral of a function f of x dx from b to a, what you get is the opposite of the integral that you would have gotten by simply switching the upper and lower limit of integration. So if you switch b and a and make it a to b instead of b to a, you get the opposite of the integral that you would have gotten here. Okay. Now, geometrically, it's not easy to see why that's the case, but if we go straight to the definition of the definite integral, it is pretty easy to see why that happens. So starting with this integral on the left, the integral from b to a of f of x, by definition, is equal to the limit as n goes to infinity of the Riemann sum from I equals 1 to n of f of xi star delta x. The f of xi star is not really going to matter here. The delta x is what makes this thing happen. How do you define delta x? Well, delta x is equal to my upper limit of integration minus my lower limit of integration divided by n, a minus b over n. That's what it is by definition. But if I were to factor a negative out of this term, the a minus b is going to become a b minus a. And that negative can be brought all the way outside of the limit because it's like a -1. It's a constant. By doing that and switching the order of the b minus a here, what I have with this limit is the limit of a Riemann sum where b is now my upper limit of integration and a is now my lower limit. And the negative that's left on the outside here gives me my end result. Okay? A similar property is this one. If I take the definite integral from a to a, so if my upper and lower limit of integration are exactly the same, then the integral will always come out to 0. And that's not that difficult to see if you think of this as an area under a curve. Again, let me see if I have a good picture to use. Wait. Yeah, to go back to my very first page just to use a graph. Normally I'm integrating over an interval from a to b where a and b are not equal to each other. But if I brought b down until it overlapped with a, then I'm squeezing this area down to nothing. So it kind of makes sense that it should become 0. But from the definition, it's also easy to see why that's the case. From the definition, delta x in this case would be a minus a over n, which is just 0. So the definition of the integral, this should be an a right here. The integral from a to a of f of x dx is equal to that same limit that shows them at the definition, but this delta x is equal to 0. And 0 times this function will also be 0, which means I'm looking at this sum from I equals 1 to n of the number 0. That's adding 0 up n times, which is still going to be 0 regardless of how big n is. So that comes out to 0. Okay? Other properties of the integral that we have are similar to what we saw with summations. 2 through 4 here are similar to what we saw with summations. Together, properties 2 and 3 are called the linearity property of the integral, which is it's not super important that you know that term here, but if you eventually get to the point where you take linear algebra, this will come up again there. So the integral of a sum of two functions is equal to the sum of their integrals. That's what that's saying. You can pull constants out of integrals like we did with summations, and the integral of a difference is equal to the difference of those integrals. All of these properties, 2 through 4, are a direct consequence of their corresponding properties for summations, and we're going to see the proof of one of them on the next page. This one right here is interesting. It's the integral of a constant. The integral of a constant function c over the interval a to b is just equal to c times b minus a. And this little graph right here explains why that's the case. Constant functions, when you graph them, look like horizontal lines. And if I want the area under a horizontal line over the interval from a to b, that region will look like a rectangle. The height of that rectangle will be c, and the base of that rectangle will be b minus a. Multiplying those gives me the area of a rectangle, and so that's why we get that result. Okay, that's really useful, and we'll use that in an example in a minute. Here's a proof of property 2 on the previous page. If I want the integral from a to b of the sum of these two functions, f plus g, by definition, that would be this limit. Notice that my f of x, my plus g of x, become f of xi plus g of xi. We're using right endpoints here. That's why you're not seeing the star. Now, if I were to distribute the delta x into each one of these and then use the sum, the property of summations that allows me to write this as a sum of two summations, this will become this. Then using my limit property to distribute that limit into each of these summations gives me this. But each of these limits independently are integrals in their own right. So that's where that comes from. Okay. Let's do an example where we're going to evaluate the integral of a polynomial without going through all of the effort that we did in that one really long example we did in a previous video. So in order to do this, I need a couple of results. First of all, I need this. I need to know what the integral from 0 to 1 of x dx is. And I can do that one geometrically. Okay, the function y equals x is a line with a slope of 1 passing through the origin. That's y equals x, right? And if I'm integrating this function from 0 to 1, then the region whose area I'm looking at is a right triangle. This triangle will have a base of 1 and a height of 1. So the area is equal to 1/2 times base times height, or just 1/2. So that tells me, just using a geometric formula, that the integral from 0 to 1 of the function x dx is just 1/2. Okay? The other thing I need is the integral from 0 to 1 of x squared dx. We evaluated this in section 5.1. We've already done this one. We found that it was 1/3. Okay? I need those results. So now let's use our properties to evaluate this integral. The integral from 0 to 1 of 2x squared minus 4x plus 3 dx. I have a difference and a sum all occurring in this integrand here. And according to my properties, this should be equal to the integral from 0 to 1 of my first term, 2x squared dx, minus the integral from 0 to 1 of my second term, 4x dx. Remember that dx needs to make it into each one, plus the integral from 0 to 1 of 3 dx. Notice that my limits of integration are staying the same, 0 to 1 each time. Okay? Now, in this first integral, I have a constant times a function, 2 times x squared. And one of my integral properties allowed me to pull constants out. So this is equal to 2 times the integral from 0 to 1 of x squared dx, minus, I can pull a 4 out, 4 times the integral from 0 to 1 of x dx, plus, now this is a constant function, and remember, we had a property on the previous page that said the integral of a constant function is equal to the constant times b minus a, which is 1 minus 0 in this case. Okay? Now, the two integrals that remain are the ones that we know values for here and here. So this is equal to 2 times 1/3, because that's what that integral equals, minus 4 times, this guy came out to 1/2. 3 times 1 is 3. So what we have here is 2/3. This is minus 2 plus 3, so that'd be plus 1, coming out to 5/3. Okay? Notice we didn't need to use the limit definition at all. We just use a couple of results one of which was easy to find using geometry, and one of which we just had already found in a previous section, and then use the properties that we covered to do the rest of the work for us. Those properties are extremely useful. We're going to talk about some more properties. So here, if I'm taking the integral from a to c of f of x dx, and adding to that the integral from c to b of f of x dx, that's equal to the integral from a to b of f of x dx. Notice the a and the b that appear here and here are the lower and upper limits of integration in my result, and the c is just any other real number. Now, it's a little bit involved to prove this in the most general case, but if we make the assumption that a is less than b, and c is some number between a and b, then it's actually pretty easy to visualize why this is true. This region right here, its area is the integral from a to c of f of x dx. This region right here, its area is the integral from c to b of f of x dx. And the sum of these two areas together makes the area of this entire region, which is the integral from a to b of f of x dx. That's what this is saying. So you can think of each of these integrals as like two pieces of the overall area, which we're adding up to get the overall area. Okay? Let's use this in an example. Suppose we don't know what the function f of x looks like, but we have a little information about it. So let's suppose that the integral from 0 to 8 of f of x dx is equal to 20. The integral from 3 to 8 of f of x dx is negative 6. We would like to evaluate the integral from 0 to 3 of f of x dx with just this information. Well, that property on the previous page would tell me this. The integral from 0 to 3 of f of x dx plus the integral from 3 to 8 of f of x dx would be equal to the integral from 0 to 8 f of x dx, okay? It's because these threes match, which allows me to piece these together into one integral. Two of these values I know. I don't know the first one. The integral from 0 to 3 of f of x dx is equal to, plus the integral from 3 to 8 of that function is negative 6. So plus negative 6 equals the integral from 0 to 8 of f of x dx, we're told is 20. Okay? If I add 6 to both sides, I'll have what I'm looking for. That would be 26. Okay? Notice we were able to do that without knowing what f of x was. We just used the properties. Last thing we want to talk about, comparison properties for the integral. So this one says if the function f of x is non-negative, if it's greater than or equal to 0, over the interval a, b, then the integral from a to b of f of x dx is going to be non-negative as well. And that goes right back to the assumption that we were making in 5.1, where we restricted our functions to be non-negative functions. And that makes sense. This function right here, which is actually, this is the image I'm using for part A, but if you notice the function y equals f of x is non-negative. It's completely above the x-axis on my interval here. So all of that area is going to be counted as positive, which is basically the same thing as what this is saying. Okay? Another example, another property, if f of x is greater than or equal to g of x for this interval from a to b, then the integral from a to b of f of x dx is greater than or equal to the integral from a to b of g of x dx. What this is saying is if I have a function, this guy up here, and this guy down here, so let's say that that one is f of x, and this one is g of x. And let's suppose a and b are here and here. So I have this guy, okay? F of x is greater than or equal to g of x on that interval. In fact, I drew it so it's strictly greater than, but I could also say greater than or equal to. The area under the curve of g of x from a to b would then be completely contained in the area or the region beneath f of x. So it makes sense that the area of this region would have to be smaller than the area of this much larger region. Okay? Geometrically, that's what this is saying. Finally, part 8 says that if f of x is between little m and big M for all x in my interval a, b. And what this would mean is that little m is an absolute minimum of f of x on that interval, and big M is an absolute maximum of f of x on that interval. Then I get this interesting little inequality. M times b minus a is less than or equal to the integral from a to b of f of x dx, which is less than or equal to big M times b minus a. Don't memorize this in terms of this inequality. It looks too messy and involved. The justification for it is actually quite simple. So look at this function right here, y equals f of x, okay? Over this interval from a to b. The integral of f of x from a to b is it's going to be the area underneath that entire curve. Now, little m and big M, where do we get those from? Well, on this interval from a to b, little m is the absolute minimum of that function. I could see that this is the lowest point that this curve attains on that interval. And so the horizontal line y equals m is going to be a horizontal line that's tangent to that point right there. Similarly, big M corresponds to the absolute maximum of that curve. It's the highest point. Now, what does M times B minus A represent? Little m. Well, little m would be the height of this rectangle right here, and b minus a would be the base of that rectangle. So m times b minus a is exactly the area of this small rectangle. But notice by the way that little m was chosen, that small rectangle is completely contained within the region underneath the function f of x on the interval a, b, which means that that rectangle is going to have a smaller area than this integral represents. Similarly, big M times b minus a, if this is big M right here, b minus a would be the base of this rectangle, big M would be the height. So big M times b minus a is the area of this large rectangle. And notice that the large rectangle contains the region whose area is given by this integral. So that rectangle would have to have a larger area than that which is represented by this integral. And that's where this inequality comes from. So let's apply this to an example that's straight out of your book. And this will be the last thing that we need to do in this section. We want to use property 8, the property we just discussed, to estimate the integral from 0 to 1 of e to the negative x squared dx. There is a reason why we're using this integrand. E to the negative x squared would be the integrand in this integral. The reason for that is because this is a special type of function which resists the fundamental theorem of calculus. And again, we have not talked about the fundamental theorem of calculus yet, but we did allude to it earlier where we said that it's going to give us the ability to evaluate integrals, definite integrals, without needing the limit definition. It makes it much, much easier to evaluate integrals. But it turns out that even with the fundamental theorem of calculus and any other techniques you come up with in calculus 2, none of them work on this function. Okay, so estimating an integral like this is oftentimes the best that we're able to do. Now, the property required us to find an absolute minimum and an absolute maximum of our function. And if you were to graph e to the negative x squared, you would see that it's a decreasing function on the interval from 0 to 1. Look at the curve. If it's decreasing, then it's going to attain its maximum at the left endpoint of this interval, because everything after that is going downhill. Similar reasoning would say that the absolute minimum of this function on the interval from 0 to 1 would be attained at the right endpoint, which is 1. And again, because we're going downhill, downhill, and downhill, nothing would be any higher than that point at the right endpoint right there. So what is f of 0 and f of 1? Well, f of 0, if I'm calling this f of x, is equal to e to the negative 0 squared, which is equal to 1, okay? And that would be equal to my maximum, my absolute maximum. F of 1 is equal to e to the negative 1 squared, and that's not negative 1 squared, it's 1 squared, and then I make it negative. So that's equal to e to the negative 1, which is 1 over e, or I'm going to say that's approximately, if I work that out, I had that written down somewhere. Where is that? E to the negative 1 is approximately 0.367. That's what I'm going to be thinking of as little m. Okay? So according to property 8, little m times 1 minus 0, that's b minus a, we're using that property right up there, is less than or equal to the integral from 0 to 1 of e to the negative x squared dx, which is less than or equal to big M times 1 minus 0. But 1 minus 0 is just 1. Little m was about 0.367. Big M was equal to 1, so 1 times 1 is just 1. That is my approximation. Notice I'm not approximating it by any specific real number. I'm saying that the actual area of the region beneath the curve given by y equals e to the negative x squared over the interval from 0 to 1 is somewhere between these two numbers. Okay? That's going to wrap things up for 5.2.